All right, so today we're going to apply what we've learned about proportions and use them to ultimately solve for missing side lengths and similar figures. But before we can do that, we have to determine whether two shapes are indeed similar. So, similar figures are formed when we have two shapes that are the same shape, but their size is proportional. So there's that buzzword, proportional. That's how it connects with what we've been doing for the last week or so. So we just talked about congruent shapes that are the same shape and the same size. Here, obviously, we have the same shape, but they're not the same size. However, we're going to determine whether their side lengths are proportionate to each other. Before we talk about their side lengths, what can we say about their angle measures? They appear to be what? The same, proportional, one smaller, one's larger. What would you say? Yes, sir?
One smaller, one's larger.
Okay, let's see. I am going to actually come out of this PowerPoint. Some text will come up, and that's okay. But I'm going to pick up this triangle, put it on top of this one to see if so far that angle is the same. Let's look at this one down here. The angle is actually supposed to be the same. And obviously, there's a right angle here, and all right angles, we haven't talked about them, but who can tell me the measure of a right angle? Just tell me. I see lots of hands. 90 degrees. So it is the same. It's the same. So you will find that though the sides are proportionate, the angle measures are the same. Because you can take a square, all angles in a square, how many degrees? 90 degrees. So if I have a teeny tiny square, all of its angles are 90 degrees. If I have a square as tall as I am and the side lengths are the same, all of the angles inside are still going to be 90 degrees. It's just the lengths of the sides that are proportionate. That's a good thing to know. So similar figures, the side lengths are proportionate. However, the angle measures are the same. So we're going to determine whether these two triangles are not congruent, but whether they are similar. And we do that by setting up a proportion with the side lengths and then using that property of cross products. So we have these two side lengths. By the way, this is a tidbit of information. This is a right triangle. Does anyone know what the longest side of a right triangle is called? Yes, sir?
The longest side of a right triangle is usually called the angular side.
Okay, the angular side. Awesome. I'm thinking of another word that starts with an H. Yes, sir? The hypotenuse. Oh, thanks. You said it nice and phonetically. The hypotenuse. It's always going to go opposite or be opposite that right angle because 90-degree angle in a right triangle will always be the largest angle. The largest side is always going to be opposite it. All right, so we've got these two hypotenuses. Hypotenuse. We're going to set up a ratio comparing those two sides in the larger triangle to their corresponding sides in the smaller triangle. So in other words, 12 is to 9 in the large triangle. There's our ratio. As 4 is to 3 in the smaller triangle. And notice 12, the length that is 12 inches corresponds to the length that is 4 inches. The length that is 9 inches corresponds to the length that is 3 inches. And then from here, we are going to use our cross products. Let me try to shrink this screen so that I can circle the diagonals. I couldn't without popping it up. That's okay. 12 times 3 is what?
36.
Just tell me. 36. 4 times 9 is 36. And since their products are the same, those sides are proportionate. These triangles are similar.
So basically all we have to do is find the proportion.
You're setting a proportion to prove that these shapes are similar. Let's look at one more example. So we'll set up our ratios. Our ratio is that hypotenuse over that bottom leg. We call them leg if it's a right triangle. So 6 inches over 5 inches, that's our ratio for the larger triangle. We're comparing it to 4 inches and 3 inches. We'll circle our diagonals to find our cross products. By the way, this entire ratio should reflect the large triangle. This entire ratio should reflect the smaller triangle. Notice my largest side length for both is up top. The smaller side length for both is on the bottom. And obviously 6 times 3 is 18. 5 times 4 is 20. They are not equal. So because these cross products are not equal to each other, that means that these shapes are not proportionate to each other, and therefore they are not similar. And then here we have yet another example. 2 rectangles. We're going to set up 2 ratios to determine whether or not they form a proportion. 20 is to 16. Those are both of those side lengths on the larger rectangle. As 5 is to 4. Those are both those corresponding sides on the smaller rectangle. We'll take our cross products, multiply them, and 20 times 4 is 80. 16 times 5 is also 80. Their cross products do equal. They are similar. Now, let's take that same skill and apply it to these rectangles when we have an unknown side. These are similar figures, so you're given that they do form a proportion, and we're going to use what we know about cross products, what we know about proportions to solve for the missing side length. So in this case, that longer side and the larger rectangle can still form a ratio with a smaller side on that large rectangle, although this time we don't know what that smaller side length is. So we're just going to use an X to represent it. We do have both measures in the smaller rectangle, so we can form that ratio. However, this time when we go to find our cross products, the best we can do is 15 times 4, which is 60. And we're going to set 5 times x equal to 60, or just 5x equal to 60. This is a one-step multiplication equation. And 5 divided by itself is 1. Who can tell me how many times 5 goes into 60? This you should be able to do without a calculator, because it does go up to your knowledgeable facts. Try to know 12 times 12. That should be one we have committed to memory. TJ? What? Well, 12 times 12 is 144. You're right. And then 5 goes into 60 12 times. Whoops. That was a little quick. And let's look at one more example. Here we have a triangle. So we're going to set up those proportions. These are similar, so there's no guesswork in that. They are similar triangles, therefore their angles are the same. Their side lengths are proportionate. So 10 is to 8, as some unknown side is to 4. Actually, it looks like this time we compared the hypotenuse in the larger triangle to the hypotenuse in the smaller triangle. the longer leg and the larger triangle to the longer leg and the smaller triangle. And we will find our cross products. And what's our value for x? Yes, sir?
5.
5. We're going to divide both sides by 8, and x is equal to 5. Okay. And that is how you find the missing side lengths and two shapes that are similar to each other.